长，然后我就搞不清楚。搞不清了，那15个分的分错。哎，懂了，这我搞不清了。我们以后要分 fundamental A 到 Z，A 最高。还要讨论什么？这是讲什么 ？Structure.
I guess I didn't really have anything specifically prepared, but as I have I guess the overall topic I thought it would be interesting to discuss would be what would it mean for us to design RL algorithms that optimally, efficiently exploit structure that arise. And I do feel like it matters a lot in order for it to be useful to practice and applications. I feel like it would be important to pick what kind of structure and understand what kind of structure is actually significant, that if we were as a community to be able to figure out and solve, like, how do we, if design RL algorithms and efficiently exploit that structure, like that could actually translate to something useful in practice, because a lot of interesting applications fit in it. So I guess maybe one question would be, what are applications or that we could kind of brainstorm that have some kind of structure where we could spend a bit of time to think about what is the relevant structure and how do you formulate that structure in some notation that means something to MVPs. So I guess applications that exhibit. So I guess here I was thinking more just, I feel like we do need a bag of applications that to start with to motivate what kinds of structure are significant. And I guess so maybe the second question then would be, what are the types of structures that arise? And maybe here, maybe, are there any connections to existing algorithms? And what are the open problems?
I see.
And I think in this space, there's also not only existing algorithms, maybe we want to understand existing, whether there's possible to get more instance dependent lower bounds as well. Because or not just instance dependent, but maybe like class, subclass, or subclasses. Ideally, we want to understand. So I feel like this has there's been a lot of really interesting development in linear function approximation that I feel I find very inspiring, and I'm wondering whether we can do that for other classes of MDPs to really understand both the hardness of exploiting that structure and what optimal algorithms would look like. And so I'm happy to hear that. If people want me to kick off with something, I have been thinking about a particular type of low rate structure that I'd be happy to hear people's feedback on, but I also want to just open it up.
I think you should start that.
Okay, I'll start there. So I guess maybe one kind of structure that I've thought about a little bit is kind of low rank. And here, I think I'm actually been thinking about a very slightly different. Well, it's actually a little bit more restrictive than just assuming the linearity in terms of the linear, like the typical formulation for linear MDPs, in particular here. I'm looking, for example, one assumption would be that there is some, let's say, here, low dimensional representation of the features, of the states and actions, such that the optimal key function of the key function of the optimal policy is lowering with respect to this feature representation. So if I was in a tabular setting, so in the tabular setting, S by A, it just means that I can factor my my key function, the optimal policy to something that's, let's say, E. Actually, maybe I'll use R because that's good. Alternately, so I would say maybe the distinction I want to make between this model is that in the linear MVP setting, there's the assumption on linear for the transition. So, okay, sorry, I should say there's. Actually, let me put down the second assumption. So the second assumption, I'm going to say low rank on the transition tensor. So here, you can think of your tensor or your transition kernel as a tensor and look at the Tucker rank. So think of I take my tensor and I can flatten it in 3 different ways. So I can flatten it along each of the 3 modes and look for what's the dimension of the column space. And the dimension of the column space will be the corresponding kind of ranks along each of these 3 modes. And if these dimensions, the column space of this tensor along each of these 3 unfoldings are kind of small, then this is low rank. This is a low Tucker rank, or this tensor has low Tucker rank. So I think maybe this one might be easier to see. So in particular, the corresponding features here, then we can think of it as you would probably have a phi as maybe a phi prime, S prime. Okay. So again, where this would be R1 dimensional, this one would be R2 dimensional, this is R3 dimensional. If you have a structure like this, it means that you can write your tensor like this way, where I can write it in a decomposition where there's a core tensor. This is a core tensor, which is R1 by R2 by R3. And each of these are the latent factor matrices. That would be something like S by R1 to be S by R2, A by R3. And so this is a little bit more restrictive of a linearity structure compared to like the assumption that my transition kernel looks like, I guess, something like V of S prime and phi of SA. I'm not sure if this, so I think this is kind of a assumption that's familiar in for linear MVPs. And I think, having low tensor Tucker rank in all 3 modes additionally means that this representation of the state action, the joint state actions, this part also factorizes, and this is lowering itself. So I've been thinking about this type of structure where these are unknown, phi and size are all unknown, but you have a guarantee that this rank does not grow with the same function.
And so if we take, for example, a tabular MVP case, then maybe you have a generative model, start with something really simple. Then you have the low rank Q star assumption, and you would want the sample complexity not to depend on S times A, but it to depend on S plus A times R or something like that.
Yeah, so ideally.
So that's a trade-off.
So you
yeah.
kind of want to go from something that looks like S times A to R times S plus A.
Yeah.
Is what like the goal is, I
Yeah.
think, in terms of what you would hope for. And I think, well, I got interested in the space because I've worked on matrix estimation before, and you can show if I in classical setting where if I just have some matrix is low rank, and I get samples from the matrix, then you can show that indeed the number of samples that I need is really is pretty tight up to R times S plus A, maybe with some log.
Don't you need though some extra conditions?
So and there's a couple of extra conditions you need. So maybe I'll say what's maybe classical matrix estimation. Here you have some matrix M. Think of like maybe I'll do a maybe easier one. Let's say my observation M is the expected value plus some independent, let's say Gaussian, zero noise, and let's say each entry is observed independently with probability P. This is an easy problem, and furthermore, you actually need one more condition. One more condition is that this matrix. So usually the conditions like this. I'm not going to define it too vigorously, but there's additional condition called incoherence, and I think incoherence here is some, I guess informally speaking, means that you can't, I guess, signal can't be too concentrated on a small subset of entries. So this condition is to say, because I'm sampling each entry independently with probability P, there's some randomness in my sampling with size sample. So if my signal is too concentrated on a small subset, and I just don't see that subset, then I'm going to be in trouble. And so this incoherence kind of means that the signal is kind of spread everywhere in a nice way, so that when you have random sampling, you get to see all the signal that you need to recover. So I think there's a lot of, so obviously many of these pieces are completely violated in RL. There's no independence. So okay, so let me actually map it to RL here. So maybe what you might want is some notion that at some, like maybe let's say I have some, just even think of like I have some, well, so I have some, I want to estimate the Q function for some policy pi, and what I really want is Q star, right? And first of all, the location of where my samples are observed is definitely, it's not going to be, it may not be independent depending on the policy you choose, because you don't, well, okay, so here I think is this part of it where you're sampling observations independently probability P. I think in RL you have to ask like what is your do you have a generative model where you can actually choose where you're sampling? If you have a generative model, you can choose where you're sampling. You could implement something like this. If you don't, then you have to deal with the fact that your samples are potentially very non-uniform, especially it could be concentrated on a few states, and there's a question of what does that mean to the low rank if some of the structure is in the states that you don't visit. This noise part is also an issue because here my estimate, I have some Q hat or estimate at a particular location. And if you add like how much does Q hat deviate from the thing I want to estimate, first of all, it's definitely not unbiased. So it's not mean zero, definitely not mean zero. And this part of it, in fact, is actually also not, it's heteroscedastic in that the variance is very different across entries. And even in that case, it's in the classical setting, it's kind of difficult to efficiently figure out estimation in kind of stochastic settings. And incoherence is also feels really weird because if I had an optimal function, optimal value function, it feels like it could be a setting where it's like some kind of sparse setting where certain few of the states contain all the reward and a few actions contain all the reward. And so you really shouldn't expect anything like this, right? So I think
that's the biggest problem.
This is a very big problem. And I think there are some reasons why this is the type of assumption looked at in matrix estimation, and it's because the goal in matrix estimation oftentimes say the goal might be something like I want to minimize m hat minus the expected value of m, and I want to estimate, let's say minimize something like, let's say the mean squared error, right? So that would be like this now. If I want to estimate something like this, which minimize something like the global error, then I do want this notion that I want to recover the entire matrix. But in RL, this is not my goal, right? My goal, I mean, this is not my goal. My goal is not to recover the whole case function. I really just care about, did I estimate the region of the matrix that is relevant to my optimal policy law. And so I think there is an interaction between the objective and the kind of conditions. So this incoherence comes specifically out of that objective. There is some work on like if I wanted to instead minimize weighted Frobenius norm, you would end up, you can relax, you get a weighted version of incoherence or a weighted version of like sampling conditions. But I think, so let me tell you about an algorithm that has been proposed for this setting. I guess something I think is interesting about it. It's a very simple algorithm. I guess so this is the algorithm in maybe it's in an algorithm. I believe it's I might be, and I remember these two, I kind of.
I think it's Zhu and Yang.
Thanks.
Yeah.
Yang?
Yeah.
Thank you. It is Zhu. I think, I guess. And the algorithm goes like this. It's a loop. So if you sample, I'm going to give the tabular version of the algorithm. Oh, actually, here, I should mention their algorithm is infinite horizon discounted. Generative model. Star is low rate. They actually have continuous state and action space plus the shifts. They also have this last condition. I think I'm not going to really look at this continuous part of it, but there's an extension to continuous to smoothness. And what the algorithm looks like is it kind of samples. It chooses a subset of rows and a subset of columns. Think of this as your states in action. So they have a set of anchor states and a set of anchor actions. And for the set of anchor states, they sample every single action. And then for the set of, and then for all other states, they sample all the anchor actions. So the sampling pattern looks like this. I should mention that this kind of sampling pattern also does really well and has nice properties for classical matrix estimation.
How are you getting samples from Q star?
Oh, samples from
Just estimate.
this is not they're not sampling from QStar, thank you. They're sampling the transition, like okay, so it will look like it's their kind of they're kind of iterating. Okay, equals the reward. T. So it's they're using the samples to construct this part of it. So this is empirical expectation from samples. They only use this to construct the estimate for, when I say samples, I should, okay, this was a bad way to say it. Okay, so let me say this. For each state and action in the special states, this the and I'll draw the picture here.
Sure.
So for each one of these states and action pairs in this special set, I'm coloring here, they sample endpoints from the transition kernel, use those endpoints to estimate this empirical or to estimate the expectation, but they're iterating on their estimate of the previous value. But actually, it's discounted, so they should be like this. This is discounted, yes.
Okay, so you're kind of building like a sparse model.
And then, so they're only estimating this for these points here. And then they estimate, let's say, for all other states and actions, then the way those states and actions are sampled or estimated is, I should, I'll draw a picture. So if I'm at this state and this action, there's this special corner where everything is sampled. I'm going to call this part, I guess, Q sharp. And then there's these parts are also sampled. I'm going to call this, I guess, X. This are this one is vector alpha. This one is the beta. Or maybe Y. And the estimate for Q hat looks like this. where this part is the pseudo inverse of Q sharp. This one is a vector X. This one is vector Y. And I know it looks really weird, but the easy way to explain it is for rank 1. Rank 1, and I should say this is the R, this is the R body. R.
Nice.
You choose R special states and R special actions.
Nice.
And in the for rank 1, so rank 1, this looks like Q hat equals S A equals Q hat S O. Like Q hat S A sharp, Q hat A sharp, the A Q hat S sharp, A sharp for rank 1. So for rank 1, the this pseudo inverse is just means that you're dividing by the corner points. And these 2 points are these two, X and the Y. And you can see that if it's rank 1, right, this would have the latent factor for S times the latent factor for A sharp, times the latent factor for S sharp and the latent factor for A. And the bottom is the latent factor of S sharp times the latent factor of A sharp. So these two cancel out. And you get, the hope is that you want this to approximately be what you want to estimate what your, right? So you set this thing, to be your estimate for Q at SA. If you had, if these were actually true samples from a low rank matrix, this would be exact. But the reason why they use this particular estimator is that they can construct error bounds for this one. Versus a lot of the tools in classical matrix estimation, it's actually very hard to get entry-wise bounds. Versus you can get entry-wise bounds for a very explicit estimator like this one.
Okay.
And so, this is a long-winded summary of their algorithm to say that what's interesting is so they show a sample complexity, and they show a sample complexity that looks like R times S plus A over epsilon squared, which is what you think you should get, right? The one thing that's kind of hidden in an assumption somewhere is that this is for gamma less than like fixed constant. So think of this being like, I don't know, less than 0.4 or something. I don't know. So it's for gamma being something small. It does not actually, the reason why it doesn't actually, the analysis does not extend to longer horizons. And it is because when you do the analysis of how the errors propagate, there's this quadratic form makes the bias blow up in a weird exponentially. So the way that they have to clamp it down is to say that, well, my gamma is small enough to offset the amplification, like the bound and the error here, so that I still get a contraction. But if gamma is not small enough, then I don't get a contraction when I do this, and then you don't have the result you want. And the interesting thing is we actually did construct an example of a setting where Q star is not, Q star is low rank, but the transition kernel is not low rank, and just apply their algorithm for a finite horizon setting, and it does blow up exponentially. The error in this estimate. So in particular, if you want to track Q star minus Q hat, and I should mention this V at every point is the max for all action Q hat. So when you I think, yeah, so it is interesting that empirically, it actually really does, it can actually blow up exponentially in the horizon lane if you are not more careful.
Yes. How do you, maybe this is an obvious question, but how do you pick those prioritized states?
Here, how they pick it is, so they suggest, so first of all,
That's
they're,
related to me to this question of like where you expect the signal to be.
yeah, they pick it spaced out because they have a Lipschitz condition, and so the main thing that they want their choice of states and or states and actions to kind of be spread out so that you're trying to get as diverse of a set as possible.
And then use Lipschitz to kind of interpolate.
Yeah, so I mean, I didn't say they have, so I explained this in the tabular setting. They actually talk about it in the continuous state action space setting, but it's, I mean, there's an additional piece that's really interesting about their algorithm where they do a discretization, like they discretize a space to a tabular setting, do this, and then extrapolate out again. And as you run it, you make the discretization grid finer and finer. And so then you can use it to show guarantees that are not just for.
But for the tabular case, it would be just uniform random choice.
Yeah.
It's kind of a good function.
Yeah, for a tabular case, you should just do uniform random. But again, your hope, I think you would probably need some condition. Like there needs to be some condition like this that if you sample uniformly random, that you pick a set of rows that spans the space and a set of columns that span the space too. So in particular, they do have a condition that your choice of rows and columns, like this matrix here has to be rank R, has to be full rank. Otherwise, I mean, it is a pseudo inverse, but it really needs to be full rank.
So what is a Lipschitz vector exactly? Like,
Oh, well, this is only because they're looking at continuous state action space. So think of your states and actions being embedded in a metric space, and then it's the Q star function is the but in the tabular setting, yeah. But I think that so some things I have a I guess I made a small comment about what we've kind of played around with this model a little bit and have some preliminary results, but a lot of questions, I think. I think, so maybe the first comment is that if you assume low rank transitions, in terms of this particular form of low rank transitions, then their algorithm, so algorithm from Charles, it does get a sample complexity of y times plus a h cubed over epsilon squared. So so if you like this distinction of imposing low rank on the transition tensor, not just Q star, is important. And so I should have commented that.
Is it in their paper or?
No, this is something that my student showed. And we don't have it posted anywhere, but we kind of ran through the calculations analysis, and it's not in their paper, but this is something that.
And then you don't need this extra condition on Q. The corner being full rank.
You do still need, so you still need, the only thing you still need or we still use all of, okay, so.
Because that's a weird assumption. I mean, like.
Yeah, we still need it, and it's because of the estimator is still this one. And if it's the way, I mean, the rank, like, I guess the reason why you need it is to argue that when you compute this quantity, okay, so maybe one way to explain what happens if it's not true. What happens if it's not true, if these columns don't span the column space and these rows don't span the row space, is that the component of the column or row space that's orthogonal to what it spans, you're not able to estimate the effect of that
Right.
component. And so then you are, yeah, so, I guess it would show up as a bias term. And if you want to actually make that go to 0, you would probably have to argue that maybe over time, when you iterate this many times, that bias that you accumulate from possibly sometimes you don't have full rank, you incur bias in that time. But when you sum that bias up over the iterations, it doesn't happen too often, so that you can still converge to an epsilon policy. Yeah, so right now this one is a weird condition. I completely agree.
Yeah, I wonder whether that would actually impact sample complexity. So that this very nice R times S plus A would be ruined, and maybe we're back to R S times A.
Right. I mean, I think that the natural fix is you just sample R prime, and the main thing is that you want to sample a large enough set of rows and columns that expands.
Yeah.
And then you would get dependence on R prime there instead. If you're in a case when it's like really sparse, there's only like this special row that is completely orthogonal to all the other rows, you would probably be in trouble.
Then prove a lower bound that this is not possible.
Yeah, so I would be very interested in the lower bound. I think one thing that is a question to me is that although there's really interesting and nice lower bounds for the linear MVP setting, but if I look at them, even though they show exponential in the dimension, like here in the R, it's exponential in R, but linear in the size of the state action space, right? So at the end of the day, all the lower bounds, even for linear MVPs, wouldn't be able to say something meaningful by this setting, because we really want to ask when does the lower bound is something that's larger than S plus A. And I mean, I think there's a lot of strong things about these models. Like you need a generative model. This is a very weird sampling pattern. Like as in, can you design a low regret algorithm? I don't know.
Father. We can't do the generative setting. It will be even harder to do.
Yeah, and if you don't have generative, then we don't have any idea. Also, one thing that's slightly more relaxed would be, suppose you don't have a generative oracle, but you have a uniform sampling oracle. So it feels like maybe uniform sampling oracle might be powerful enough, because matrix estimation, all you need is uniform samples. I'm not sure if that's really.
But my understanding is that even for the generative case, the question is not resolved because there is this weird condition.
This condition, that's true.
So that's just not really the result that one is hoping for.
Yes, yeah. And
like uniform sampling wouldn't give you much, because I could just pad a bunch of states that are 0 value. And then
that's true.
you would only see those most of the time. It's still low rank, it's just zeros.
Oh, okay, yeah. So you're right. So I guess you're right, because this incoherence and the uniform sampling really interact with each other. And that if you have something like incoherence, it means that your signal is spread everywhere. Then that's kind of what motivates uniform sampling, because it means you're getting all the signal. Like if your signal was concentrated on one row or column, you have to somehow guarantee that you sample that one, right? And which would not be uniform. You're right. But that would be the challenge of. I mean, that is the challenge of RO, right? Is exploration, and it would really get around. And I think we also in this preliminary work with the students, we also showed, I guess, 2 more there's also, I guess, another algorithm. This other algorithm is kind of, I guess I can mention later. But this other algorithm, which is slightly different than this one, just by a little bit, you can get kind of Q star low rank. So without the condition on the low rank transitions, you can get a sample complexity. Oops, sorry. You can get a sample complexity of this h to the sixth, which I mean we weren't very happy with the h to the sixth, but at least it doesn't blow up. That's actually the hardest. And the second thing we could show is that if Q star is low rank plus min gap bounded away from 0 by delta, then we can get a sample complexity that looks like h to the 4. But this algorithm is also really weird, and so it's not something I'm really happy with either. And I'll tell you, oh, go ahead.
H to the 6 doesn't bother me that much. If you can get the R times S plus A,
Yeah, so we can get it.
no with conditions like
You
the one in the
still,
shop.
you still need those conditions.
Oh, okay. Okay.
Yeah, you still, I mean, I don't know how to get around this condition.
Yeah.
I don't know how to get around this condition,
Mhm.
is a good question.
I see.
So we're basing somehow the necessity of the incoherence condition on matrix estimation, but then we're allowing ourselves a generative model. Like if we were allowed to do active sampling with
Yeah.
rank 1 matrix estimation, like we can find, even if it's one sparse, we can find that entry in sample complexity just to test the same. I mean, I understand here the transition kernel and the Q are interacting, but
Yeah.
the necessity of incoherence isn't that clear when you make the analogy to matrix estimation, because
That's
this
true.
is the active sampling.
You're right. But the tricky thing I think is that suppose you had active sampling and you knew where the signal was, then you're good. And in particular, that is a result in the classic matrix estimation literature that you can get rid of incoherence, but you have to, by having a sampling pattern,
Yeah.
where the sampling probabilities are constructed as a function of the coherence parameters. It's kind of really weird. I mean, right, which is cheating, kind of.
Oh, no, I'm saying even more than that. I'm saying the sampling pattern is constructed as you observe the matrix. So
Oh,
like if I have a rank 1 matrix, imagine the entries are positive, I just have to find the maximum entries. Like I can just keep going and like, peel off one of the left values, one of the right values at a time, and then find the maximum entry in just S plus A. So like
right,
don't
but I
have
mean,
to-
if you had like a really bad setting where it was like totally sparse like this, like 1 and 0s everywhere, then you would still be like, you'd have to hit that point, right? So if it's really, really sparse and you're trying to find this one point, you're still kind of in trouble. So there needs to be, I mean, I think low rank itself can't be enough of a structure. It needs to be low rank plus something. But I don't know what the something, what would be a reasonable something? Like I agree, this is not like the fact that this corner matrix needs to be low rank, that doesn't seem to be the right kind of assumption, because it's really.
So the
And-
incoherence scores for the sparse example is just going to tell you to sample in that one spot, right?
Well, yeah, exactly.
It's-
So if
it's
you,
kind of trivial.
exactly, so it's kind of silly, right? So if I knew this incoherence scores, it would tell me where the signal is and I just sample, right?
Yeah.
But that's like, that's cheating because we don't know where the signal is, right? So,
Is there a sense in which you can say if you don't know where the signal is, and like looking at that example, like it actually is the best uniformly? Like, is that something you believe, or you think active sampling? Or like on some.
I think that there is benefit to the game because our objective is not this, right? Like our objective is not to estimate the whole matrix, it's to estimate the large entry. So there should be something that we can like that we should be able to relax something here.
So the
because we don't care.
Rincon Bandit, we had some
Yeah.
papers that you can push through. It's very special. I don't know how to generalize exactly that problem. It's like searching for the peak. It's kind of like a random subsampling of rows and columns, and then some elimination algorithm.
But then you're gonna get stuck with the same example.
No, because like, so what happens is that you see all these zeros, and from that, you know that, okay, like the corresponding marginals sort of have to be zeros. And then you're not sampling there anymore. So you're gonna sample somewhere else.
That's what I thought. So I mean, are you saying you can get
You
extra
can.
say on this?
Yeah.
Yeah, that's what I thought initially.
You can.
Okay.
Active sampling does work on it.
So you can peel off the.
Yeah.
Okay, so then
You kind of
information is
sample
not-
in the middle, and then based on sampling in the middle, you make inferences on the marginal, and that's enough to
and you just
eliminate
eliminate-
enough, push the probability mass out of the bad parts, because you're only searching for the maximum of this unimodal function. That's not the same as estimating all the matrix. We're just trying to find the needle, but it's unimodal, so it's like it's a nice structure. It's like this one-dimensional case. I don't know how to do it.
Maybe a
Then
question
two
is like, is there, like, when you say it's not incoherent, is there like some special structure that you might expect in the unknown, like spatial structure? Very.
Yeah, I also wonder if something can be like even like if there could be some relaxed notion of like local, like it's like you only care about the regions of the state space that you visit or that you care, you know, the whole policy cares about.
Well-
you don't need to.
Until we prove a law, but we shouldn't rule out that it's possible to do it.
But I do.
I
think-
wouldn't rush with these extra conditions. It's
Yeah.
just have to, yeah, think some more.
But I would definitely be super curious of getting a lower back here too. I'm not sure what that would look like.
Have you looked at empirical examples, like what does the structure of the Q matrix look like?
Yeah, so this group, Child's group actually have done some empiricals. And they have actually shown empirical, like positive results in the empirical work for. They have done like matrix estimation plus RL for Atari games and looked at like some of them are actually RLOA. They had looked at some simple control problems that they did the pendulum one. So there are some problems that definitely act, where I would argue, yeah, maybe even the transition is long range, not just the Q star. Like the examples actually might have this additional. As well. But their empirical results actually look pretty promising.
I'm thinking about that. This Q star realizability is hard. A lot of cases when things are just linear. And here there are many more unknowns. So I don't know whether. So for example, if phi was known and psi is unknown, that's going to be a hopeless case, I think. And like,
Say it
how
again.
does it work? So if phi is known
Oh,
and psi is unknown, then that's just a linear case. So just if you have linearly parameterized Q star, it's a very, it's okay. So the basis functions have some extra structure. So you have to reason about that the hardness example still goes through. It's hard work.
no, I think the hardness examples for linear MDP don't, oh, I see, you're saying,
Not linear MDK.
Here you're allowing
I
S
see, I see.
dependence.
Huh?
Here you're allowing S dependence.
Yeah, you're allowing,
In the lower bounds,
Yeah.
S dependence is too much because it's
What?
exponential indeed. It's different quantities.
No, well, yeah, sure. I mean, sure. If you want to learn both phi and psi, you should allow S and A dependence for sure.
oh,
But if I say that phi is given to you, then the S dependence should be gone.
Yeah, you should just have linearity.
And if that would be hard,
Oh.
then
Yeah.
then the whole problem is gonna be hard if
Yeah, yeah, that's like a.
given to you.
uh-huh.
Let's think about that.
Maybe like you did mention, if you have some spatial structure, you can have something that might be more reasonable that can replace something, replace this condition. Or something that's more motivating. That can replace that condition. Yeah, but this is get like good modal structure, for example. That. But I feel like unimodal is still. That's too strong.
Sorry, something I missed, I think. What is the metric in which you're measuring epsilon in all of these results?
Oh, this is, I think it's that you get an epsilon optimal policy, but it's, I think it's with the, for every, like you get a V, your estimate for V hat of S minus V star S. has to be that.
For every
I want to make sure that. It is for.
Many times though, these you get the same results for relaxed conditions too. So things do not get easier if you have a fixed initial state.
So what kind of a structure assumption do you need to ensure the Q star is low rank? So that's the say reward and transition are both low rank, that's imply.
Oh, that's sufficient, yeah. If transitions are reward are low rate, that's sufficient. But I don't,
Not the sum of two low rank reward, a low rank matrix, that's.
I mean, it would be that you would
that's
have
low rank.
like a sum of rank R plus another rank R would be bounded by rank 2R.
Oh, yeah, that makes sense. Yeah,
Uh-huh.
and another question is regarding on the sample complexity, why is there an S instead of the size of the anchor states?
Because you are still, like for the special set of anchor states, you're sampling all the actions, but for every state, you're sampling anchor states, the anchor actions. So you still have, you still incur linearness. Are you asking why you incur linearness as opposed to?
Oh, I'm thinking maybe if you can reduce S to the size of the anchor states, then
Oh, I mean, you can't here because the anchor states are just like the set of states that kind of span the rose space, but you still need to learn for the other states. So for the other states, I need to learn like how is this state related to the set of inferences? So for the set of anchor states, you have set of anchor states times A, but for the other states, you just have a set of anchor, all states times only the anchor actions. So what you're gaining is that you're not saying you need to have a multiplicative cost between these actions.
Is it related to the Flambe paper? So they are just trying to learn the representation, but they assume there are just a finite number of possibilities of the feature mapping.
Oh,
Sorry,
say it one more time.
the name is Flambe, FLAM.
Oh, Flambe, yeah, okay. You said the paper by when?
I mean,
And-
yeah. If you apply here, does it?
Sign is different. Here is.
They have they assume a computation oracle where you're
Right.
solving for Emily, and I guess that's.
I think that's not the problem. That's fine. We don't care that much about computational efficiency. But I think that the log coordinate might kill you because you might need to enumerate too many of these maps to have some cover. And then the S times A, they come back.
Yeah, but if you have like smooth feature or some structure on the feature, then the cover number might be smaller than. Yeah.
That's additional assumption.
Yeah,
on the top of
additional
us down here.
That's true. I guess maybe whatever first one. Looking at the covering of how many of the representations.
Did they take the product of the two spaces and take the log of the coordinate of that space, and that is going to scale with S times A. Because one scales
They have a product.
with S, the other scales with A. Take the product, you're doomed.
That's true. Yeah.
It's a very cool set of problems.
That's all I talked about.
That was very cool. Thank you.
Ideas. Happy to hear.
I think you gave us a lot of homework.
可以太早。4点。我决定不做。没。OK。没错。